Over the next 7 days, the United States is about to experience a weather collision. Winter storms, dangerous ice, tornado threats, and near-record heat will all unfold back-to-back, and the first system begins tonight. The models still don't agree on where the freezing line sets up, meaning a small temperature shift could change everything. At the same time, a total lunar eclipse rises over North America, and clouds from this storm train may block it for millions. This isn't just active weather, it's a compressed high-energy transition week, and the uncertainty may be the biggest warning sign of all. If this week has you watching the sky a little differently, hit subscribe because this pattern is not done, and neither are we. Drop a comment below telling me where you are watching from and whether this storm train is affecting you personally. And if you want to help the Skylab grow, share this one. You are the reason we can keep doing this. We will see you in the next one. Now let's get into it. The storm has already started, and the most sophisticated weather prediction systems on the planet cannot agree on what happens next. That is not a minor footnote. That is the entire story. Because right now, on the evening of March 1st, 2026, a winter storm is sliding across the central United States. And the two most trusted forecasting models in the world, the American GFS and the European ECMWF, are showing solutions so different from each other that forecasters at the Weather Prediction Center are openly hedging their language in official outlooks. At day 1 to 2 lead time. That almost never happens. When meteorologists start hedging at 24 hours, that is not a technical curiosity. That is a warning. Here is why it matters. The difference between a catastrophic ice storm and a forgettable rain event is sometimes 1 degree Fahrenheit at the surface. 1 degree. The freezing line, that invisible boundary where precipitation transitions from harmless rain to sheet ice, is sitting almost perfectly on top of one of the most populated corridors in the central United States. Right now. Kansas City, St. Louis, central and northern Kentucky. Millions of people are living inside the margin of error of a forecast, and the models cannot even agree where that margin falls. Think about what that means for the people who have to make decisions based on these forecasts. Salt crews for highway departments cannot pre-treat roads for uncertainty. Either you lay brine and it washes away in the rain, or you hold back and the roads glass over in 45 minutes. Aviation planners at hub airports in Chicago and Cincinnati have to decide hours in advance whether to pre-cancel flights. Power utilities across the Ohio Valley are looking at 2 completely different scenarios, one manageable, one not, and they have to staff and stage equipment for both simultaneously. This is not a weather problem, this is a resource allocation problem, and the atmosphere is refusing to give anyone a clean answer. The meteorological mechanism driving this uncertainty is something called a warm nose, a shallow wedge of above freezing air that rides aloft while a thin layer of Arctic air clings to the surface beneath it. Precipitation falls through the warm layer, becomes liquid, then refreezes as it passes back into the cold air at the surface. Whether you get snow, sleet, freezing rain, or plain rain depends on the exact depth and temperature of that surface cold air layer. A few hundred feet thicker, a degree or 2 colder, and you get snow. A few hundred feet shallower, and the freezing layer vanishes entirely. There is a legitimate scientific debate right now about whether models are systematically underperforming in these so-called amplified split-flow regimes, patterns where the atmosphere is doing several contradictory things at once. And as you are about to find out, contradictory is exactly the word for this entire week. The question no one has fully answered yet is whether the uncertainty is the anomaly, or whether the uncertainty is actually the forecast. 30 miles. That is the difference between a weather inconvenience and a weather disaster in this storm. And right now, 30 miles is well inside the cone of uncertainty. The battleground zone for Storm 1 stretches from central Missouri through southern Illinois and into the Ohio Valley. And inside that corridor, the atmosphere is about to do something that makes winter precipitation forecasting genuinely one of the hardest operational problems in all of meteorology. It is going to produce narrow, intense bands of precipitation driven by a process called frontogenesis, the sharpening of the temperature gradient at the leading edge of the storm system. When that sharpening happens in the presence of a coupled jet streak aloft, the atmosphere essentially creates a focused conveyor belt of rising air. Moisture feeds up into that conveyor, saturates, and dumps. not gradually, not evenly, in stripes. We are talking about the possibility of snowfall rates approaching 1 inch per hour in isolated mesoscale bands that may be only 20 to 40 miles wide. On one side of that band, it is raining. On the other side, people are under winter storm warning criteria, and the exact placement of those bands will not be known with confidence until the storm is essentially happening in real time. This is the narrow corridor problem, and it is not new, but it is particularly acute this week because the atmospheric energy driving it is unusually high for early March. The temperature gradient across the central United States right now is sharp enough to be drawing real attention from forecasters who track these setups. Elevation matters here too. Small terrain features that normally go unnoticed, the gentle rise of the Ozark Plateau, the Ohio River Valley floor, can pin that freezing line in place or nudge it north or south just enough to flip an entire county from rain to heavy ice. And then there is the urban heat island factor. Cities generate enough residual warmth from buildings, pavement, and human activity to push surface temperatures a degree or two above their rural surroundings. St. Louis proper might stay a degree above freezing while the suburban ring ices over. That sounds like good news for the city. It is actually a nightmare for road crews whose treatment zones straddle that exact boundary. The infrastructure backdrop here is not neutral. This January of 2026, a single winter storm placed 230 million Americans under some form of weather alert simultaneously. 230 million. That is roughly 2/3 of the entire United States population. The systems that serve those people, power grids, highway departments, emergency management agencies, are already operating in a state of accumulated stress. They have not fully recovered, they are not starting fresh, and now the atmosphere is reloading. What comes after the reload is the part that should genuinely concern you. Here is the deceptive part of this storm, and it is worth paying very close attention to because this is where public perception and actual risk tend to diverge the most dangerously. The ice totals from Storm 1 are mostly going to come in under 1/4 of an inch. That is below the threshold for an official ice storm designation in most warning criteria frameworks. If you scroll past the forecast graphic quickly, you might conclude that this is a minor event. You would be making a mistake. 1/10 of an inch of glaze ice, a layer you could almost mistake for frost if you were not paying attention, is enough to make an untreated road surface essentially frictionless. Not slippery, frictionless. The physics become brutally unforgiving. A vehicle moving at 30 miles per hour on a glazed surface has almost no meaningful ability to stop or steer. That is not hyperbole. That is the reason 1/10 of an inch of ice consistently produces more traffic fatalities per precipitation event than 6 inches of snow does. But the ice threat this week is not just about roads. The trees are the problem. Across New England and the Mid-Atlantic, the nor'easter that preceded this system dropped over 30 inches of snow in some locations. 37.9 inches recorded at Warwick, Rhode Island, and wind gusts reached 83 miles per hour at Nantucket. The trees in these regions are already stressed. Their root systems are dealing with saturated, partially frozen soil. Their canopies absorbed enormous mechanical loading from that prior storm. Now a new system is moving through, and even a light glaze of ice adds weight. Not a lot of weight. Enough weight. The difference between a branch that holds and a branch that snaps onto a power line is sometimes measured in fractions of an inch of ice accumulation on top of existing snowpack. Power utilities in the Northeast are acutely aware of this. The concept in infrastructure planning is called cumulative fatigue, the idea that a system weakened by a prior stress fails at a much lower threshold the second time around. And the freeze-thaw cycles that come with transitional March storms are particularly destructive to utility infrastructure, because the expansion and contraction of ice inside joints and connectors degrades them in ways that do not show up until the next mechanical stress arrives. FEMA issued disaster declarations for Mississippi and Tennessee after the January sequence. That context is still fresh. And here is the question that the operational meteorology community is quietly beginning to ask out loud. Are our warning thresholds, which were largely designed around single, isolated events, still appropriate for a pattern that is delivering back-to-back impacts without recovery windows in between? The answer to that question may determine how well prepared millions of people actually are for what is building behind this storm right now. While the cold side of this system is dropping ice across the Ohio Valley, something else entirely is happening 300 miles to the southwest, and it is the part of this week that transforms a difficult stretch of weather into something genuinely extraordinary. Thunderstorms are already firing across Kansas, Oklahoma, Missouri, and Arkansas. Not winter thunderstorms in the marginal sense, actual convective cells, driven by Gulf moisture that is moving north at a pace that is unusually aggressive for the 1st of March. Dew points, the measure of atmospheric moisture that severe weather meteorologists watch most carefully, are creeping northward into regions that should still be locked under late winter dryness. The Gulf of Mexico is functioning right now as a moisture pump, and the split jet stream configuration overhead is giving it a clear channel to deliver that moisture directly into the heart of the country. This is the reload and fire mechanism, and once you understand how it works, the rest of this week snaps into focus. The jet stream is not a single river of fast-moving air. In a pattern like this one, it splits into two distinct branches, a northern stream that is driving Arctic air southward across Canada and into the northern tier of the United States, and a southern stream that is drawing warm, humid Gulf air northward and providing the energy source for storm development. When those two streams interact along their boundary, they do not just produce one storm. They produce a sequence, a storm train. Each disturbance that moves along the jet produces a new low-pressure system, each one dragging cold air on its backside and pumping warm, unstable air ahead of it. Storm 1 is tonight. Storm 2 is March 3rd through 5th. And the models are already beginning to sketch the outline of something more significant in the March 10th to 11th window. That last one is too far out for confident specifics. But the pattern itself, the configuration of ridges and troughs that drives these setups, is not showing any signs of breaking down. This is not a week of bad weather. This is the atmosphere entering what meteorologists sometimes call a high-amplitude regime, a state where the contrast between warm and cold, wet and dry, winter and summer becomes so sharp that the energy available for storm development increases with every cycle. The gradient sharpens, the storms intensify, and the compression between events leaves no recovery window for infrastructure, emergency services, or the people who depend on them. Storm 2 is already taking shape, and it has a different character than Storm 1, less ambiguous on the cold side but more dangerous in ways that a lot of people are not going to be watching for. Storm 2 arrives in the March 3rd through 5th window, and at first glance it looks less chaotic than Storm 1. The models are in better agreement. The track is more defined, and for parts of New England, the snow totals, 3 to 6 inches across a broad swath, sound almost routine after the nor'easter that dumped nearly 40 inches in some locations just weeks ago. But routine is exactly the wrong frame for what is happening here, because Storm 2 is not arriving in a vacuum. It is arriving on top of an already stressed system, and the cumulative impact of back-to-back events is one of the most consistently underestimated risks in operational meteorology and emergency management alike. The snowpack across New England is still substantial from the prior nor'easter. Urban snowpack, the dense, compacted, partially refrozen mass of cleared snow that piles up along city streets and in parking lots, has a distinct effect on local thermal gradients. It keeps surface temperatures lower than they would otherwise be, which means the freezing line sits slightly further south, which means more of the precipitation from Storm 2 falls on the cold side of that boundary. That is a small effect in isolation. In a stacked impact sequence, it matters. The icing threat with Storm 2 extends from North Carolina to New York along a narrow band that tracks the warm nose position. Again, we are talking about sub-quarter-inch totals in most locations. Again, that is enough. The melt-refreeze cycles that accompany March transitional storms are particularly punishing on road surfaces already cracked and saturated by winter. Bridges and elevated roadways are the first to ice and the last to clear. The aviation system, which took 9,000 plus flight cancellations in a single day during the January sequence, will be looking at another round of cascading delays. The critical question with Storm 2 is not what happens on the cold side. It is what is simultaneously building on the warm side. Because while the northeast is managing ice and snow, the atmosphere 3 states to the south is doing something that has nothing to do with winter and everything to do with what severe weather season actually looks like. And if you are watching the Storm Prediction Center's extended outlook products right now, you have already seen the signal. Something is being flagged for March 5th, and it is not a winter weather advisory. On the night of March 3rd, something is going to happen in the sky above North America that will not happen again for nearly 3 years. A total lunar eclipse, the full passage of the moon through Earth's shadow, the event that turns the moon a deep copper red and earns it the name Blood Moon, will be visible across the entire continent. Or it would be, except that the cloud shield from Storm 2 is going to be sitting directly over much of the viewing area at exactly the wrong time. Tens of millions of people who would have had a clear view of one of the most striking celestial events in recent memory may instead be looking up at a low grey ceiling and seeing nothing at all. That sounds like a minor disappointment in the context of everything else happening this week. But consider what it actually represents inside the central narrative of this entire stretch of weather. The storm train does not care about the eclipse. The atmosphere does not negotiate. A pattern that is already compressing winter, spring, and near summer into the same 7-day window is now adding a third dimension. It is pulling the sky itself into the collision. The same system that is stressing power grids, snarling air travel, and forcing emergency managers to make impossible resource allocation decisions under uncertainty is also on its way past erasing a celestial event that took the entire geometry of the solar system 3 years to set up again. There is also a geomagnetic footnote worth mentioning. A coronal mass ejection, a burst of solar plasma from the Sun, is arriving in roughly the same time frame, triggering a G1 geomagnetic watch. Let's be clear, there is no established scientific mechanism connecting solar storms to tropospheric weather. The physics do not support it. But the visual, a blood moon rising during a geomagnetic disturbance behind a storm cloud that itself is the product of an unusually high-energy atmospheric collision, is the kind of coincidence that reminds you how many systems are running simultaneously above your head at any given moment. Every single one of those systems is under stress this week. The eclipse disappears behind the clouds. The storm continues south, and what it finds there is already waiting. The Storm Prediction Center does not issue a categorical severe weather outlook for Day 5 lightly. When forecasters in Norman, Oklahoma look out 5 days and decide the atmospheric signal is clear enough to draw a slight risk polygon on the map, they are telling you something important. The confidence threshold has been crossed. The atmosphere has shown its cards early enough that they are willing to put it in writing. That polygon for March 5th covers the Dallas-Fort Worth Metroplex, sweeps through Texarkana, and extends to Little Rock, Arkansas. Damaging winds, large hail, tornado potential on March 5th, in what is technically still meteorological winter. Here is why this matters beyond the immediate threat. Day 5. Slight risk is not issued based on hope or extrapolation from vague signals. It is issued when the thermodynamic and kinematic ingredients, the instability, the wind shear, the moisture, are already present in the observational and model data in a way that gives experienced severe weather forecasters real confidence. The Gulf moisture we discussed earlier, the same moisture that is complicating the ice-rain transition further north, is also loading the lower atmosphere across Texas and Oklahoma with dew points and instability values that belong in April or May, not March 1st, not even close to March 1st. The thermal gradient driving this setup, the temperature contrast between the Arctic air mass sitting across the northern plains and the near summer warmth already baking South Texas, is functioning as an energy source. The sharper the gradient, the more potential energy the atmosphere has to convert into storm motion, updraft intensity, and the rotating supercells that produce the most dangerous, severe weather. Right now, that gradient is exceptionally sharp. What makes early March outbreaks historically notable is not just the timing. It is the combination of factors that align differently in early spring than in peak, severe weather season. Upper-level winds are often stronger in March than in May, which means storms that do develop carry more wind shear and can produce more intense rotation. The atmosphere is not at peak instability. Summer heat contributes more raw CAPE, the measure of convective available potential energy, but the wind profile more than compensates. Early March tornadoes have caused significant casualties in the historical record precisely because the public perception of severe season lags behind the actual atmospheric calendar. Meanwhile, 600 miles to the north, people are scraping ice off their windshields. Same week, same country, same atmospheric engine running two completely different programs at once. And if you think that contrast is extreme, the extended models are showing something for the March 10th to 11th window that raises this entire week to a different level of concern entirely. Imagine a single storm system capable of generating blizzard conditions across the northern plains and a violent tornado outbreak across the southern states at the same time. On the same day, under the same low pressure center. That is what some extended model guidance is sketching for around March 10th to 11th. And even with all appropriate caveats about extended range forecast uncertainty, the signal is worth taking seriously. This is called a dual threat day, and it is not as rare as you might think in the historical record. It is, however, one of the most operationally challenging scenarios emergency management systems face. Because the resources that respond to blizzards and the resources that respond to tornado outbreaks are not the same resources. They are not staged in the same locations, and they cannot be easily redirected once they are committed. A National Guard unit deployed to clear roads in Minnesota cannot simultaneously pre-position in Arkansas for post-tornado search and rescue. The specific signal in the models right now shows a strong low-pressure system developing near Iowa in the March 10th to 11th timeframe in some guidance runs. To the north and northwest of that low, drawing down Gulf of Canada and Arctic air, blizzard criteria winds and heavy snow across the Dakotas, Minnesota, and Wisconsin. To the south and southeast, ahead of the warm front, the same Gulf moisture that has been fueling severe weather all week is now fully engaged with upper-level wind profiles that support supercell development. The overlap zone, the area where both threats are simultaneously plausible, covers a significant portion of the central United States. Now here is the critical disclaimer, and it matters. Day 10 forecast models carry substantial uncertainty. The precise track of that low-pressure system will determine whether the dual-threat scenario materializes exactly as sketched, or shifts north or south, or weakens entirely. The atmosphere at 10 days is not a certainty. It is a probability distribution, and the distribution right now has a meaningful cluster around a significant event. But here is what is not uncertain. The pattern itself. The jet stream configuration that is generating Storm 1 and Storm 2, and the March 5th severe outbreak does not break down between now and mid-March in any model guidance we can access. The storm train keeps running, the gradient keeps sharpening, the reload mechanism keeps cycling. Whether the March 10th event is exactly as dramatic as the early guidance suggests or somewhat less so, the compression of impacts is real, the cumulative stress is real, and the temperature swings driving all of it are the most extreme the country will see all year. Early this week, wind chills across the northern tier of the United States, Minnesota, the Dakotas, northern Wisconsin, and Michigan are dropping below zero. Not the air temperature, the wind chill. The felt temperature, which is the temperature that actually matters for exposed skin and exposed infrastructure. Pipe freeze thresholds, livestock vulnerability, black ice formation timelines. By the end of this same week, South Texas is recording low temperatures in the low 100s Fahrenheit, 100 degrees, in March. The Gulf Coast Corridor, Louisiana, Mississippi, Alabama, the Florida Panhandle, is looking at high temperatures in the 90 to 100 degree range. The Midwest, sitting between these extremes, is projected to reach the 40s and 50s, 15 to 30 degrees above seasonal normal. In a single week across the same country, the temperature range spans roughly 140 degrees Fahrenheit from coldest to warmest observed values. Let that number settle for a moment. 140 degrees of temperature variation, from below zero wind chills in the north to near triple digits in the south. That is not a weather pattern. That is a collision between seasons that normally happen months apart, compressed into the same 7-day window. For the energy grid, this creates a demand flip that system operators describe as one of the most stressful scenarios they manage. Heating demand is peaking in the northern tier, while air conditioning demand is rising sharply in the south. These are different parts of the grid, different generation resources, different transmission corridors. The system is not designed to maximize both simultaneously, and the rapid swing from one extreme to the other, cold early week, warm late week, means utilities have almost no ability to gradually transition between modes. They have to pivot hard, fast, and with limited margin for error. For agriculture, the freeze-thaw cycling this week could not arrive at a worse time. Winter wheat across the plains is approaching the green-up stage, where it loses its cold hardiness and becomes vulnerable to late freezes. Orchards in the Mid-South are watching for frost damage on early buds. The same pattern that is generating blizzard conditions in the north and near summer heat in the south is simultaneously threatening two distinct agricultural windows simultaneously. And the gradient itself, the temperature contrast that makes all of this possible, is not incidental. It is the engine. It is the energy source that every storm this week is drawing on. Everything happening this week flows from a single atmospheric structure. A deep trough, a southward dip in the jet stream anchored over the western United States, an amplified ridge, a northward bulge, building over the eastern Atlantic. Between them, a split flow pattern that is locking the entire storm train in place like a track that cannot be moved. Western trough dominance is the technical shorthand. What it means in plain language is that cold air from the Arctic is being efficiently channeled southward across the Rocky Mountains and into the Central Plains, while simultaneously the ridge to the east is blocking the pattern from progressing. Storms do not move cleanly from west to east the way they do in a more progressive flow. They develop, intensify, and then stall or loop, drawing additional energy from the gradient before finally clearing out. And while one storm is clearing, the trough is already generating the next disturbance. The split flow adds the second ingredient. The northern jet branch manages the cold air delivery. The southern jet branch manages the moisture transport from the Gulf. Where those two branches interact, the battleground zone we have been discussing all week, is where every significant weather event this week is occurring. The freezing rain corridor for Storm 1, the icing swath for Storm 2, the severe weather outbreak for March 5th, the potential dual threat event for March 10th. All of them are products of the same jet stream configuration. There is a broader research question embedded in this pattern that the atmospheric science community is actively debating. Amplified jet stream waves, configurations where the north-south amplitude of the jet becomes unusually large, appear to be occurring with greater frequency in recent decades. The mechanism proposed by some researchers involves Arctic warming, reducing the temperature gradient between the pole and the mid-latitudes, which weakens the polar vortex and allows the jet stream to meander more. This is not a settled scientific consensus. It is an active area of research with genuine disagreement among experts. But it is worth noting that the configuration driving this week's storm train is exactly the type of amplified, persistent wave pattern that sits at the center of that debate. What is not debated is the consequence. When this configuration locks in, it does not produce a single event. It produces a sequence, and every event in the sequence hits a system already weakened by the one before it. The same atmospheric engine that is generating snow and ice across the central and eastern United States is simultaneously loading the warm sector with moisture levels that forecasters are flagging as anomalously high for early March. Precipitable water values, the meteorological measure of total atmospheric moisture from the surface to the top of the atmosphere, expressed as the depth of liquid water that column would produce if it all rained out at once, are running significantly above climatological normals across the Gulf states and lower Mississippi Valley. These are not minor anomalies. The values being observed right now belong to May or June in the historical record. They are showing up in early March because the Gulf of Mexico is warm. The southern jet stream branch is providing an efficient moisture transport pathway, and the atmospheric circulation has been drawing tropical and subtropical air northward for days. On the cold side of the storm train, elevated moisture translates directly into heavier precipitation totals. The same narrow snowbands we discussed in Storm 1 are capable of producing those 1 inch per hour rates precisely because the moisture available to the storm is higher than a typical early March system carries. On the warm side, elevated precipitable water values mean that convective storms, thunderstorms, supercells, squall lines will have more water vapor to work with, which increases both the rainfall intensity and the hail growth potential within individual storms. There is a third consequence that tends to get far less media attention than the storms themselves: the snowmelt. Snowpack across the Ohio Valley, the lower Great Lakes states, and parts of the Mid-South is substantial. When the warm sector of Storm 2 moves through and temperatures spike 20 to 30 degrees above normal in the span of 48 hours, that snowpack does not just melt gradually, it releases rapidly into river basins that are already running at or above normal levels from the January event sequence. Add heavy rainfall in the warm sector on top of rapid snowmelt across frozen or saturated ground, and the flooding risk this week is not a secondary story. It is arguably the most underreported primary threat in the entire pattern. Flooding kills more Americans per year than tornadoes, hurricanes, or blizzards. Year after year, the statistics are consistent, and year after year, flooding receives a fraction of the media attention that the more visually dramatic weather events command. This week, the flooding threat is significant, and it is structural. The river basins across the Ohio Valley and lower Mississippi drainage system are entering this storm sequence already primed. Soil moisture is high from the January events. Snowpack is adding a water reservoir that will activate quickly when warm air arrives. And the warm sector precipitation associated with Storm 2 and the March 5th severe weather system is projected to deliver heavy rainfall, not in isolated convective cells, but in widespread organized precipitation patterns across regions that have almost no additional absorption capacity. Flash flooding in the warm sector is the immediate concern. Urban areas are particularly vulnerable. Stormwater infrastructure that was designed for typical rainfall intensity events struggles when heavy precipitation arrives on top of already saturated drainage systems. The streets flood before the water can route out, underpasses fill, low water crossings become traps, and the critical safety failure mode for flash flooding is the one that makes it so consistently deadly. People underestimate depth. 12 inches of moving water can knock a person down. 24 inches can float most vehicles. The water that looks passable from the driver's seat is frequently not. The river flooding concern has a longer timeline. The Ohio River and its major tributaries, the Wabash, the Kentucky, the Green, require days to weeks to respond to upstream precipitation events. The snowmelt and heavy rain falling this week will be moving through those systems into late March. Communities along the lower Ohio and the upper Mississippi should be watching stage forecasts closely, because what is falling now will arrive downstream on a schedule that does not respect the news cycle. Infrastructure that was flagged in the January disaster declarations, stormwater systems, culverts, low-lying road sections, is again at risk. The compression of this storm sequence means that some of those systems will face a second significant challenge before they have been fully inspected or repaired from the first one. And this brings us to the question that this entire week of weather actually forces us to confront, not just about forecasts and storm tracks, but about what we have built, how we have built it, and whether it was ever designed to handle this. 230 million people under simultaneous weather alerts, 9,000 plus flight cancellations in a single day, National Guard units activated across multiple states at the same time, FEMA pre-positioning resources in the southeast before the storm made landfall. That was January 2026. That was 6 weeks ago. The infrastructure serving those 230 million people did not get a break. The power lines that stayed up are still carrying the load they were carrying before the storm. The bridges that stayed open are still showing the stress fractures and frost heave damage they accumulated through the freeze-thaw cycles of January. The stormwater systems that handled the January rainfall are still functioning at reduced capacity in areas where debris and ice damaged their intake structures. The highway department workers who drove salt trucks for 72 continuous hours are back on call this week. The emergency management coordinators who ran incident command centers in January are back in those chairs. This is cumulative fatigue, and it is one of the most genuinely underappreciated concepts in disaster risk management. A system that successfully handles a major stress event is not reset to baseline afterward. It is weakened. Its failure thresholds are lower. Its recovery capacity is reduced. The next event hits a degraded system, not a fresh one, and the event after that hits a system degraded twice over. The power grid is the most visible example of this. Utility crews who have been executing emergency repairs since January are running on reduced personnel depth. Mutual aid agreements, the arrangements utilities make to borrow repair crews from neighbouring systems after major outages, have been activated multiple times already this winter, and the crews available under those agreements are not an infinite pool. When 3 regions need mutual aid simultaneously, someone does not get it. Public attention fatigue is real too. People who received emergency alerts, sheltered in place, and disrupted their schedules for the January storm are psychologically primed to tune out the next alert. This is documented in emergency management literature. The warning cry effect, where repeated warnings that did not produce the worst-case outcome desensitize people to subsequent warnings, is one of the reasons forecasters worry intensely about how to communicate escalating risk without generating either panic or dismissal. When the atmosphere is running a storm train with compressed spacing between events, both failure modes become more likely simultaneously. The system was not designed for this. Not the power grid, not the highway infrastructure, not the emergency management apparatus, and arguably not the public communication frameworks either. The forecasters are being unusually transparent this week. That sentence deserves to be read slowly. Because in the modern era of highly confident, algorithmically generated weather graphics, the open acknowledgement of uncertainty by operational meteorologists at the Weather Prediction Center is not the default. It is a deliberate communication choice made when the situation genuinely warrants it. The problem is that the public communication infrastructure built around weather forecasting was not designed to convey meaningful uncertainty. The icons on the weather app on your phone do not have error bars. The 7-day forecast graphic does not show you the spread between the GFS and the European model. What you see is a single deterministic output, partly cloudy, chance of snow, high of 37, that suggests a level of precision the underlying science does not actually support, especially in high amplitude, split flow regimes like the one dominating this week. Social media amplifies this problem in a specific and damaging way. When model guidance shifts, as it has been doing repeatedly this week, the individual model frames get screenshotted, posted, and distributed without context. A GFS run showing 12 inches of snow in a city makes the rounds on Wednesday. A Thursday run showing 4 inches gets posted with outrage framing, suggesting the forecasters were wrong or lying. Neither characterization is accurate. The model's updated because new data came in. That is the system working as designed. But the public experience of it, filtered through social media, generates genuine confusion about whether forecasters can be trusted. Into that environment, weather manipulation conspiracies reliably surface during extreme or anomalous patterns. This week is no exception. The claims are consistent. The storm train is artificial. The temperature extremes are engineered. The jet stream configuration is being deliberately manipulated. These claims have no scientific basis. The mechanisms proposed, high-frequency ionospheric research programs, contrail seeding, electromagnetic pulse technologies, do not have the physical capacity to alter atmospheric dynamics at the scale being attributed to them. The actual mechanism generating this week's pattern is the one we have been discussing, a high-amplitude jet stream configuration driven by an exceptionally sharp meridional temperature gradient under conditions that the observational record and physical theory both support fully. But here is the important point inside all of this. The reason conspiracy theories find traction during extreme weather events is not stupidity or malice on the part of the people who share them. It is the entirely rational response of a public that has been conditioned to expect precision from weather forecasts, is watching the models swing dramatically, and is experiencing atmospheric behavior that feels genuinely outside the range of the familiar. The uncertainty is real. The extremity is real. The explanation that the atmosphere is just doing physics at high energy is accurate but unsatisfying to people who want to know who is responsible for the ice on their car and the power outage in their neighborhood. Uncertainty is not incompetence. It is the honest description of a dynamical system operating at its limits. This week, the atmosphere is at its limits, and so are we. Early severe weather season activation, stronger warm surges arriving weeks ahead of historical averages, amplified jet stream configurations appearing with what seems like increasing regularity. Pattern after pattern this winter that pushed previous records into territory that required new records to describe. The temptation in moments like this is to reach for a tidy explanation, to say that the climate is changing and this is the result, full stop. That is not how the science works, and it is worth being precise about why. The distinction between a weather event, a climate trend, and an attribution statement is not pedantic. It is the difference between accurate information and motivated reasoning, and both are available right now in large quantities. What the research community can say with genuine confidence is this: the early season activation of severe weather patterns in the southern plains has been a documented phenomenon in recent years. The specific mechanism, a warming Gulf of Mexico providing anomalously high moisture values earlier in the calendar year, combined with jet stream configurations that allow that moisture to interact with cold air masses, is physically plausible and is being actively studied. Whether it represents a statistically significant trend or a cluster of anomalous years will require more data and formal analysis. What the research community is more cautious about is the amplified jet stream question. The hypothesis that Arctic warming is destabilizing the polar vortex and causing more frequent high-amplitude wave patterns is genuinely contested. There are researchers who find compelling evidence for it. There are others who argue the statistical signal is not robust and that natural variability explains the observed pattern equally well. This is not a case of scientific consensus versus denial. It is a case of a genuinely open question at the frontier of atmospheric science. What is not contested is what this week actually is, whether it is a trend or an anomaly, whether it is a new normal or a statistical outlier. The compression and the uncertainty and the cascading impacts on infrastructure and emergency management are real. They are happening right now, and they will continue to matter for everyone living inside this pattern, regardless of how the scientific attribution question eventually resolves. Everything comes back to the freezing line. That one invisible boundary, the threshold where 1 degree Fahrenheit determines whether you are scraping ice or wiping rain, is the atom around which this entire week orbits. It is where Storm 1's uncertainty is most concentrated. It is where Storm 2's icing threat will either materialize or dissolve. It is why road crews cannot act with confidence and why power utilities are staging for 2 scenarios simultaneously. The freezing line is not a meteorological detail. It is the dividing line between manageable and catastrophic for millions of people who will never think about it by name. The severe weather boundary is the warm side equivalent. 50 miles north of the March 5th slight risk polygon, people are watching snow forecasts. 50 miles south, storm chasers are checking their equipment. The same atmospheric engine running its 2 programs simultaneously has drawn a line across the map and told the geography on either side of it to have completely different weeks. And the people who live along those lines, the ones in the 50-mile corridor of maximum uncertainty, on both the cold side and the warm side, are making decisions right now based on forecasts that, by the open acknowledgement of the forecasters themselves, carry unusual uncertainty. This is what the compression does. It does not just add stress to infrastructure, it compounds the decision-making burden at every level. The individual driver deciding whether to leave for work early. The school district administrator deciding whether to call a snow day. The power utility dispatcher deciding which crews to pre-position and where, the emergency manager deciding which counties get resources in a scenario where the resources are not sufficient to cover every plausible impact zone simultaneously. Every one of those decisions is being made under elevated uncertainty, by systems already operating under cumulative fatigue with less margin for error than they started the winter with. The atmosphere is not chaotic this week in the technical sense. It is not random. It is doing exactly what physics says it should do given the configuration of pressure systems, jet stream branches, moisture channels, and temperature gradients that are currently in place. The behavior is predictable at the large scale. The storm train will continue. The gradient will sustain it. The pattern will persist into mid-March. What is unpredictable is the precise location of the boundaries. And in a system, this energetic, precise location is everything. This is the week that separates meteorological winter from meteorological spring, not with a clean line, but with a collision. Winter does not give way gradually. It fights. And the atmosphere, caught between Arctic air masses that still have energy left and a Gulf moisture source already behaving like summer, is not resolving that fight. It is amplifying it. Every storm in this sequence is the product of that unresolved tension, and every storm will continue to be until the pattern finally shifts, not because the cold winds or the warm winds, but because the gradient eventually exhausts itself. Until then, the reload cycle continues. The storm train runs, and somewhere along the freezing line in the 50-mile corridor where everything is uncertain, someone is about to have a very different week than the person 30 miles away from them. The atmosphere is not in chaos. It is in collision. And the difference between those two words is the difference between a system beyond understanding and a system that is, in fact, telling us exactly what it is doing, if we are paying close enough attention to hear it. Mid-March has not arrived yet, and the models are already showing the next signal.